To ensure the smart IoT product success, hardware testing emerges as a crucial step, verifying that the device aligns with the installed technology and meets functional requirements. Hello everyone, I'm Xing Zhang, a product test engineer at Dusun IoT, specializing in IoT hardware testing for over 10 years. Dusun IoT focuses on the supply of core embedded hardware in the IoT industry. Today, we're going to talk about how to plan a smart IoT product hardware's testing, which mainly include 5 parts: test plan development. This involves understanding the purpose and objectives of the testing plan, writing conditions, considerations, and summarizing reviews. It also includes creating a template for the plan. Test design specification. This focuses on defining the testing strategy, including methods and approaches for testing. Testing in practice. This section provides a real-world example by outlining a testing plan based on smart hardware. Devices. Management of testing issues. Here we explore the creation, handling, and resolution of testing problems. Testing summary. This part involves creating a testing operation manual and preparing case analysis reports. These modules aim to provide a comprehensive understanding of testing processes and strategies for smart hardware devices. A testing plan is a document that outlines the scope, methods, resources, and schedule of the testing activities for the entire information system, including hardware assembly and confirmation testing. It identifies what will be tested, the features to be tested, who will perform the tests, and various potential risks. The testing plan is essential for preventing risks and ensuring the smooth implementation of the plan. The purpose of the testing plan is to establish a realistic and comprehensive plan for all testing activities, including the objectives, scope, methods, schedule, and expected results of each testing activity. It also helps in organizing the project and defining the responsibilities and work content of each role in the testing project. Additionally, it aids in developing an effective testing model to accurately validate the hardware system being developed, determining the time and resources needed for testing to ensure accessibility and effectiveness, establishing the criteria for the completion and success of each testing phase, and identifying and mitigating various risks in the testing activities. The testing plan serves both internal and external purposes. Internally, it serves as the result of the testing plan for review by relevant personnel and developers, stores the details of plan execution for peer review by testing personnel, and contains additional information such as the schedule and testing environment. Externally, it provides customers with confidence by explaining the testing process, the skills of the personnel, the resources, and the tools used. It's crucial to start writing the testing plan at the beginning of the testing project. This allows leaders to make macro adjustments and allocate resources accordingly, helps testing personnel understand the overall project testing situation and the work to be done at different stages of the project, and facilitates the understanding of testing personnel's work by other team members for collaboration. The test plan is written by the experienced project test manager. Here are 6 key elements of the test plan. 5W1H. Why we're doing these tests. What exactly we're testing at different stages, when each stage of testing starts and ends. Where we keep the relevant documents, defects, and the testing environment. Who's involved in the project and who will be doing the testing, how we're going to do it, including the tools and methods we'll use for the tests. Testing plan should not necessarily be perfect, but it must be practical and tailored to the project's characteristics and the company's actual situation. It should be continuously adjusted to meet actual testing requirements as the world is constantly changing, with hardware requirements, hardware development, and personnel changes occurring. The testing plan should reflect the project's testing tasks, testing stages, and resource requirements from a macro perspective without needing to be overly detailed. After completing the testing plan, it's important to review its correctness, comprehensiveness, and feasibility. The review panel typically includes hardware developers, marketing personnel, testing managers, and other relevant project leaders. After the project is completed, it's essential to review the execution of the plan to identify any areas that were not reasonable in order to accumulate experience for writing the next project's testing plan. Here is a simple template of a testing plan. The next part, let's go through more about testing strategy. This provides recommended methods for testing the product for each type of test. There should be a testing description and an explanation of why it's being carried out. When developing a testing strategy, consider the technologies to be used and the criteria for determining when the testing is complete. Below are the considerations for each test, including the use of instruments, standards, operating methods, etc. Note: if a certain test is not being conducted, it should be explained in a sentence along with the reason. For example, this test will not be conducted as it is not applicable to this project. I will briefly outline the testing strategies for power testing, internal signal testing, functional testing, reliability testing, and long-term stability testing. Power testing involves three main types of testing: static testing, dynamic testing, and power sequence testing. First, let's look at static testing. This includes static impedance testing and static voltage testing. During static impedance testing, we use a multimeter to measure the impedance of test points to ground on the board. Some common test points include VCC3V3_MCU, VCC_5V_MCU, DCIN, DC_out, and ADC sampling points. Moving on to static voltage testing, we still use a multimeter, but we also bring in a voltage regulator. This time, we're measuring various power inputs and outputs from linear power sources on the board to check if they meet the design requirements. Now, let's switch gears to dynamic testing, which involves dynamic voltage testing and noise and ripple testing. During dynamic voltage testing, we refer to the manual for key ICs and use a multimeter and a voltage regulator to check if the voltage meets the operational requirements. This includes measuring the voltage under different load conditions such as unloaded, normal load, and full load. For noise and ripple testing, we use an oscilloscope and a voltage regulator. We want to ensure that the system operates normally with minimal noise interference. This involves testing with the oscilloscope probe and ground spring, establishing normal data transmission in each link, and setting specific oscilloscope parameters for ripple and noise testing. Voltage and current surge testing requires specific tools and conditions. The tools needed for this test include an oscilloscope and a power source such as a regulated power supply or a battery pack, considering the actual supply voltage. The test condition involves capturing waveforms with an oscilloscope when the system is powered on. Next up is the power margin testing. For this, we'll be using a multimeter, a test fixture, a computer, a USB to serial connection cable, and a DC regulated power supply. Now, let's talk about the testing conditions when measuring the highest voltage. We follow the chip's datasheet and test it at the maximum operating voltage value, which is usually around 5% higher than the typical voltage during the test. We use a serial port monitor to observe the system's startup process. If the system can start up normally, it's considered to pass this test. For the lowest voltage measurement, we gradually lower the supply voltage to the chip until the system can no longer start up normally. If, for some power sources, even after significant reduction, the system can still start up normally, we stop lowering the voltage and record the last tested voltage as the lowest voltage margin for that power source. Moving on to power efficiency testing. We calculate the output power divided by the input power and then multiply the result by 100%. Power consumption testing includes operating power, static power, and standby power for products powered by batteries. When testing static power current consumption, we need to pay attention to electrical characteristics. Lastly, we need to consider power sequence during power up and power down. It's essential to capture waveforms using an oscilloscope to ensure the power up sequence meets the design's timing requirements. That concludes our overview of the power testing process. The internal signal testing encompasses various aspects that need to be carefully evaluated to ensure the proper functioning of the system. Here's a streamlined overview of each testing aspect. Clock signal testing. This involves testing the frequency, rise time, fall time, duty cycle, overshoot, undershoot, and voltage level of each clock signal. Clock degradation testing by adding capacitance load to the clock signal. Observe if the clock slope deteriorates and affects the functionality of the respective unit on the board. Reset signal and timing testing. Measure the reset signal for each chip. Confirm the reset voltage level, effective reset time. And for reset signals with logic and timing requirements, measure the reset timing interval. Other interface and bus timing testing. All signal testing positions should be as close as possible to the signal's receiving end. Our GMII test voltage levels, timing write to registers and read from registers. IC test start and stop signals, acknowledgement signals write to registers and read from registers. DDR3 test overshoot, differential signals and single-ended signals. RS485, RS to 3 to RS4 to 2, for RS to 3 to RS4 to 2, test waveforms at the transmitter and receiver. Common test items include transmission rate, driver output voltage, driver output signal levels minimum load, driver output signal levels maximum unloaded, receiver input voltage range, receiver input threshold, receiver input resistance, driver common mode voltage, and receiver common mode voltage. UART performs system startup. Loop external RS to 3 to hardwire into internal program. Run UART test program, test waveform, and compare with the datasheet. SPI, test voltage levels, timing write to registers and read from registers. QSPI, test voltage levels, timing write to registers and read from registers. AD, DA for AD, measure effective bits, sampling rate, signal-to-noise ratio, harmonic distortion, spurious free dynamic range, channel phase error, and bit drift over time. Use measurement instruments such as logic analyzers, power supplies, and ADC testing software like Visual Analog. For DA, measure sampling rate, output signal frequency, output signal power, and spurious free dynamic range. Use measurement instruments such as 81,000 to 150 parallel error analyzers, multimeters, oscilloscopes, spectrum analyzers, power supplies, and software like DAC testing software. GPIO, test voltage levels, Ethernet, evaluate communication stability and error rate. TCP, UDP communication, utilize tools like iPerf3 to ensure it meets the bandwidth claim of 90%. Communication. These tests are crucial for ensuring the proper functioning of the internal signals within the system. For the functional testing as per the design specification, the following steps should be taken to thoroughly validate each function. Normal operation testing. Verify that each function described in the design specification operates as intended under normal conditions. Ensure that input-output relationships and system responses align with the expected behavior outlined in the design specification. Abnormal operation testing. Intentionally introduce abnormal or out of specification conditions to test the system's behavior. Verify that the system gracefully handles abnormal inputs or conditions without compromising safety or performance. Protection function testing. Validate all prescribed protection functions including overcurrent protection, overvoltage protection, undervoltage protection, overtemperature protection. EDC trigger these protection functions using simulated scenarios and verify the system's response. And recovery. Exception handling testing. Test the system's ability to detect and appropriately respond to exceptional circumstances or faults, such as sensor failures, communication loss, or power supply irregularities. Verify that fault conditions are properly logged, reported, and managed according to the design specifications during these tests. It's important to document and review the results against the expected outcomes outlined in the design specification. Additionally, the use of simulation tools, test fixtures, and diagnostic equipment is advisable to ensure comprehensive and accurate validation and functionality. When it comes to reliability testing, there are several important tests to consider. First and foremost is the climate environmental reliability testing, which includes high temperature testing, low temperature testing, rapid temperature change testing, temperature shock testing, constant temperature and humidity testing, temperature humidity cycle testing, salt fog testing, waterproof and dustproof testing, UV aging testing, and xenon lamp aging testing, among others. These tests aim to assess the product's adaptability to various environmental conditions, making them crucial methods for evaluating product reliability. The execution of these tests needs to adhere to standards such as GJB1508, GB2423, GJB4, IEC 60068, GJB1032, GJB3608, GJB322A, GJB548, GJB899, GB4208, and TB3021. Next is mechanical environmental testing, which mainly includes mechanical vibration, mechanical shock, as well as other tests such as drop, impact, and acceleration testing. The execution of these tests needs to conform to standards including GJB1508, GB2423, GJB4, IC 6068, GJB1032, GJB3608, GJB322A, GJB548, GJB899, GBOut-to1563, TB3058, ISO 16750, and others. Additionally, there is comprehensive environmental reliability testing, encompassing temperature-humidity combination testing and temperature-humidity vibration. Comprehensive testing, also known as the so-called 3 comprehensive tests. These tests need to comply with various international and domestic environmental and reliability test standards such as GB, GBOut, GJB, IEC, ISO, and MILSTD, SAE, ASTM, ISDA, JIS, IPC, JEDIC, GM, Nissan, and others. Finally, there is electromagnetic compatibility (EMC) testing, including EMI electromagnetic interference testing and EMS. Electromagnetic susceptibility testing. EMI testing covers radiated disturbance testing, conducted disturbance testing, harmonic current disturbance testing, as well as voltage variation and flicker testing. EMS testing includes electrostatic sensitivity testing, RF electromagnetic field radiation resistance testing, RF field induction conduction disturbance resistance testing, voltage transient, short-term interruption and voltage variation disturbance resistance testing, surge disturbance resistance testing, fast transient burst disturbance resistance testing, and power frequency magnetic field disturbance resistance testing. These tests need to comply with a series of reference test standards. The specific applicable test items need to be determined based on the product type and corresponding regional regulatory and standard requirements. The long-term stability testing involves simulating the equipment's operating environment to conduct prolonged stress testing. This includes simulating the equipment's maximum power consumption mode for extended stress testing, as well as subjecting the equipment to abnormal operating conditions for long-term stress testing. Additionally, The testing should simulate fault injection into the equipment for extended stress testing. These long-term stability tests are essential to assess the equipment's performance and durability over prolonged periods of operation and under various stress conditions. The long-term stability testing involves simulating the equipment's operating environment to conduct prolonged stress testing. This includes simulating the equipment's maximum power consumption mode for extended stress testing, as well as subjecting the equipment to abnormal operating conditions for long-term stress testing. Additionally, the testing should simulate fault injection into the equipment for extended stress testing. These long-term stability tests are essential to assess the equipment's performance and durability over prolonged periods of operation and under various stress conditions. When it comes to the practical implementation of testing strategies, let's take a look at an example of a testing plan for smart hardware. Know how to use hardware before testing it. Simply put, smart hardware is the fusion of hardware and applications. This innovative concept marries traditional devices with the digital realm, connecting them to the internet and facilitating control through dedicated mobile software apps. Through this integration of software and hardware, smart IoT devices enable remote control and imbuing intelligence into everyday objects. Examples of smart hardware span diverse industries, including shared bicycles, smart speakers, smart gateways, smart sockets, and more. Smart hardware spans a diverse spectrum, ranging from chips, sensors, and wireless modules embedded within the hardware, to network communication devices, servers, and an array of devices with integrated applications. Smart devices connect to the cloud primarily through four main methods: Bluetooth, Wi-Fi, Zigbee. And for G, each method has its own advantages and disadvantages, and the choice of connection method depends on the specific application scenario of each smart device. The specific differences between these connection methods are as follows. Based on the data in the above diagram, when selecting a communication method for different smart devices in practical use, it is evident that, for example, a parcel locker can utilize a 4G connection mode as it has a built-in network module, making it convenient for use in different locations and supporting simultaneous connection of multiple lockers. On the other hand, smart home devices mostly employ Wi-Fi connections, which are more convenient for use within a single local area network environment. It's essential to consider the actual usage environment, communication range, power consumption requirements, and data transfer rate when determining the most suitable connection method for a particular smart device. How does smart hardware connect with apps in today's landscape? One-click configuration stands out as the most popular method for connecting smart hardware with applications. This approach primarily leverages technologies like Smart Config, Bluetooth, Zigbee, and sound waves developed by T. Smart Config is a provisioning technology designed to connect new Wi-Fi devices to an existing Wi-Fi network by using a mobile app. Network credentials are broadcasted from a smartphone or tablet to an unprovisioned Wi-Fi device. This technology requires less knowledge of SSID or password of an access point, which is especially crucial for headless devices and systems lack of a user interface. Managed by the Bluetooth Special Interest Group SIG. Bluetooth is a short-range wireless technology standard facilitating data exchange between fixed and mobile devices over limited distances. It plays an important role in establishing personal area networks. PANs, Bluetooth hardware. Devices, such as headsets and mice, are designed to support point-to-point connections and come with stringent distance requirements on the device and the application. Zigbee is used to create personal area networks utilizing small, low-power digital radios. It is widely used in applications like home automation, medical device data collection, and other low-power, low-bandwidth needs, making it ideal for small-scale projects requiring wireless connectivity. Zigbee devices employ a mesh network of intermediate devices to transmit data over long distances. ZigBee protocols are specifically designed for embedded applications, prioritizing low power consumption and accommodating low data rates to pass certification. Individual devices within the network must boast a battery life of at least 2 years. However, it's important to note that ZigBee, not being a TCP, IP protocol, lacks direct connectivity to the internet. Consequently, a ZigBee gateway is essential for converting signals into a Wi-Fi protocol, sound wave. This method revolves around the mobile phone emitting coded and encrypted sounds. Captured by the smart hardware's microphone, the hardware then decodes and decrypts the signal, successfully configuring the device. How does that control smart hardware when the hardware is connected to the mobile application? The application will access the server interface through the internet subsequently. The server receives the request, processes the corresponding logic, and sends the response data back to the mobile app, the application acting as an intermediary, then transmits this data to the hardware directly connected to the smart device. How do smart hardware connect to the cloud? Smart hardware can establish connections with cloud servers through various methods, each offering distinct advantages and considerations currently. The primary connection methods include Wi-Fi, 4G, and Ethernet. The selection of a specific method depends on the application scenarios and the actual requirements of the smart device. Wi-Fi is a prevalent choice for smart home and office environment, while 4G is ideal for mobile environments, well suited for smart devices that require communication on the go with a built-in module. These devices can function across different locations. For instance, express cabinets utilizing for connections enable real-time communication between cabinets scattered in various locations, supporting simultaneous usage of multiple cabinets. Ethernet offers reliability and stability, and is a robust choice for smart devices that demand a higher level of network stability. As we delve into the intricate relationship between smart hardware and apps, coupled with the diverse landscape of current applications and devices, it becomes imperative to develop strategies tailored to meet the testing needs of different products. It's also crucial to recognize that smart hardware extends beyond the mere fusion of software and hardware. It encompasses the intricate interplay between intermediate networks and the cloud. This broadened scope requires a nuanced understanding of testing methods, with the testing focus extending beyond the realms of simple app and hardware testing. Embracing this complexity ensures a robust approach to quality assurance in the realm of smart hardware and applications. Testing planning and practice based on smart hardware devices. Developing testing strategies and cases mainly involves hardware testing. Testing of the interaction between smart hardware and integrated application apps, and product reliability and stability testing. Sensor testing. In the anatomy of smart systems, smart sensors play a crucial role similar to the nose in the facial features of the human body. Alongside technologies like radio frequency identifiers, RFID, barcode readers and writers, and the global positioning system, sensors work collectively to define the intricate features of the system. When testing sensors, it is recommended to evaluate the following key aspects: basic parameter, testing transmission power, sensitivity, accuracy, and stability, etc., to ensure optimal performance when delivering data to users. Performance, testing vital metrics like response time and decay time that gauge the efficiency and effectiveness of sensor operations. Environmental factors, testing temperature resistance and anti-interference capabilities ensures reliable performance across diverse scenarios. Reliability, assessing metrics such as lifespan and mean time between failures provides insights into sensors. Durability and consistent functionality, network connection testing. It is crucial to ensure that your device and network connections are always available. Therefore, there are two aspects that need to be verified during testing. Reliability. Testing focuses on preventing disruptions or data loss in normal operation. Data transfer should be coherent without interruption or loss. When real-time synchronization is unattainable, the system should ensure data synchronization within an acceptable range of user response time. Fault tolerance in scenarios where the device goes offline. User prompts must be given to inform the device status and allow users to detect it. Additionally, data added before the device went offline should continue to be transmitted and utilized once back. Online, ensuring a user-friendly experience, usability testing. Ensuring hardware usability is paramount, particularly in the pre-mass production phase. Here are some key considerations. Functional testing. Conduct a meticulous functional test, especially the Wi-Fi and Bluetooth modules in the device, to verify whether its functions are working properly. Batch testing, using a sufficient number of devices for testing, facilitate the ability to better discover potential hardware defects thoroughly. Data synchronization testing. Parallel testing across multiple devices is imperative to validate the accuracy of data. Synchronization between different devices. Fault detection and warning mechanism in the event of device malfunctions. Timely alerts should be issued. Hardware performance. Hardware performance is a critical focus in scenarios like smart home, when users frequently engage with hardware and require long-term stability. Given the indispensable role of network connectivity in enabling smart functions, hardware testing engineers are advised to assess hardware performance under challenging network conditions, including situations with weak or unstable signals. Key considerations include response time. Test the time of smart hardware responsive to instructions. Achieving a low response time ensures users get immediate feedback and excellent operational experience. Boundary testing. Evaluate hardware performance under various boundary pressure situations, network and storage constraints, etc. Assesses whether the hardware can function effectively under extreme or adverse conditions, stress. Test, simulate long-term use and repeated operations to stress test the hardware. This is particularly crucial for smart home hardware, as users frequently utilize these devices over an extended period without frequent replacements. Upgrade testing. Smart hardware operates within a complex ecosystem of multiple protocols, operating systems, firmware variations, and intricate networks. When undergoing upgrades, these combinations demand thorough testing to guarantee seamless operation and an enhanced user experience. Coverage testing. Ensure the execution of upgrade tests across different hardware versions, spanning the transition from older versions to newer releases. Verify compatibility and stability throughout the upgrade process in order to assure normal functionality post-upgrade. Cross-version testing. Conduct testing that spans multiple releases, such as directly upgrading from an old version to the latest version. This testing validates the compatibility and stability of the hardware across different software iterations. Power consumption testing. As user preferences shift towards devices that do not necessitate real-time charging, evaluating the power consumption of these devices becomes increasingly crucial. Thorough power consumption testing ensures that the device aligns with user expectations and delivers an optimal experience. Circuit testing. All functionalities of smart hardware lies in the circuits. A flawless smart hardware circuit foundation is imperative to unleash perfect functionalities and achieve performance that surpasses industry standards. Testing the circuit power, signal integrity, RF compliance. EDC stands as the cornerstone of the entire testing process. Integrated application testing. Sensors, IoT connectivity, M2M modules, and a range of components within the smart hardware are connected to the software networks, where the transmission of protocols or instruction happens. Therefore, the software testing is relatively cumbersome. Beyond conventional software testing methods like functional testing, testing, usability testing, and performance testing, the following aspects demand focused attention in smart hardware testing. Business, functional testing. Ensure the software meet business requirements and have the diversity of functionalities. Interface testing. Verify that interface returns are displayed correctly and assess the system's fault tolerance. Security and privacy testing. Address concerns related to network security, data encryption, permission protection, and privacy safeguards. Compatibility, user experience testing. Evaluate compatibility across different systems and assess the user experience. We need to check whether it is ease of use. Network testing. Validate the software's ability to meet users' needs under diverse network conditions, ensuring consistent performance. Performance testing. Thoroughly assess CPU, memory, power consumption, startup time, FPS, and other performance metrics to optimize overall functionality. For interaction between smart hardware and integrated applications, device linkage and multi-scenario interaction testing. Evaluating the device linkage and multi-scenario interaction and performance of both the application and smart hardware in diverse and complex situations is critical for enhancing user experience and functional reliability. The following are some key test solutions to ensure a thorough assessment. Communication testing in different networks. Test the communication between the app and smart hardware under different network environments, such as office networks and home networks. Verify that the devices and app can establish a stable and reliable connection and can transmit data and commands properly across different networks. Server error handling testing. Simulate server errors and observe the response of the devices and app. Test if the devices can handle server errors properly, such as using local data caching or providing appropriate error prompts. Additionally, verify if the app can handle server errors appropriately by providing clear error messages and user-friendly error handling options. Multi-user and multi-device bindings testing. Test the data transmission and command execution when multiple users are bound to one device, or when one user is bound to multiple devices. Ensure that the app can correctly identify and differentiate between different users and devices, and guarantee accurate and error-free data and command transmission. Device and app network interplay testing. Test scenarios where the device is connected to the network while the app is offline, or the device is offline while the app is connected. Evaluate if the app provides user-friendly and easily understandable prompts regarding the network state changes. Verify if the app promptly reflects network status changes and offers appropriate user feedback and options. Device status display testing. Simulate various device statuses such as busy, sleep mode, network connection errors, network switches, weak network signals, etc. Test if the app accurately displays the current status of the device. Ensure that the app correctly represents the device's different states and provides relevant user feedback and operational options. App control and device state testing. Test the app's behavior during different operations, such as killing the process, running in the background, clearing data, switching networks for devices requiring the same local network. Verify if the app can restore the connection with the device correctly after these operations, and ensure that the device responds appropriately to app commands. Interface testing. Interface testing plays a pivotal role in guaranteeing effective communication between the application, app, server, and ensuring the proper functionality of smart hardware products. Smart hardware typically manage requests from two ends. One interfaces with the app, and the other establishes a TCP UDP long connection with the server, regularly sending heartbeat packets and other communication content. Upgrade testing. When either the smart hardware or the application undergoes an upgrade, it is crucial to ensure compatibility between different versions of both components. To summarize, testing smart hardware products differs from traditional device testing, as it requires a focus on both the hardware and software aspects. The two components complement each other, and testing involves various combinations and permutations, including network interactions, which present new testing directions. Reliability and stability are critical aspects of product testing, ensuring that the device performs consistently and reliably under various operating conditions. Here are some key considerations for conducting reliability and stability testing. Reliability testing focuses on assessing the device's ability to function consistently and accurately over a specified period of time. It involves subjecting the device to different environmental conditions, such as high temperature and humidity, to evaluate its performance and endurance. Hardware testing engineers should consider industry standards and guidelines relevant to the device's usage environment. For example, temperature and humidity devices may require testing under high temperature and high humidity conditions to ensure their suitability. For door magnetic devices, there are specific requirements related to operating environments with vibrations and impacts. Stability testing aims to evaluate the device's ability to maintain stable performance over an extended period. It involves simulating specific long-term operating conditions that mimic real-world usage scenarios. Hardware testing engineers should define the desired operational environment and assess the device's performance and behavior over an extended duration. Additionally, stability testing may include assessing the device's battery life and power consumption under various operating conditions to ensure it meets the expected lifespan and power efficiency requirements. During the testing process, it is important for hardware testing engineers to record and track the bugs they discover. This not only helps in resolving the problems, but also serves as a crucial metric for evaluating the quality and output of the testing and development work. Nowadays, there are many mature issue tracking software or management systems available. Each issue follows its own life cycle, and below is a brief description of the various stages. Create an issue ticket. Specify the hardware platform or system where the issue occurred and identify the specific module or component affected by the problem. This helps in categorizing and assigning the issue correctly. Document the actions or operations performed that led to the issue. Include detailed steps, input data, and any specific conditions or settings required to reliably reproduce the problem. This helps in understanding the root cause and eventually fixing the issue. Evaluate the severity level of the issue based on its impact and urgency. Assign appropriate severity levels such as critical, major, minor, or trivial. Critical issues may like system crashes. These high-priority issues should be addressed promptly. Ensure that relevant stakeholders are notified about the issue by sending notification emails or using a notification system integrated with the issue tracking software. This helps keep everyone informed and involved in the resolution process. Record any available relevant information related to the issue, such as error messages, log files, screenshots, or any other supporting documentation. Gathering as much relevant information as possible helps in analyzing and resolving the issue more effectively. By capturing these details during issue ticket creation, hardware testing engineers can provide a comprehensive and structured view of the problem, facilitating efficient troubleshooting and resolution. Address the issue ticket after receiving an issue ticket. The following steps are involved in handling the ticket. Once the development team acknowledges the receipt of the issue ticket, the hardware testing engineers should work closely with the testing team to reproduce the issue. Once the issue is reproduced, the development team will assess its impact and severity. They evaluate the potential solutions and consider the implications on the existing stable architecture. Careful evaluation is necessary, as some fixes may have a significant impact on the stability of the system. If feasible, the development team proceeds with resolving the issue. They make the necessary changes to the software or system to fix the problem while considering the potential impact on the overall stability. For issues that cannot be directly addressed or require further investigation, the development team documents the problem and makes recommendations for future design and manufacturing considerations. This helps in providing insights for future improvements and avoiding similar issues. By following these steps, the testing and development teams can effectively handle issue tickets, prioritize fixes, and ensure the overall quality of the software or system. Closing the issue ticket. After a bug is fixed, the following steps are still involved in closing an issue ticket. The testing team needs to retest the issue by following the original reproduction steps if the problem is no longer observed and the fix is confirmed. The issue can be considered resolved. If the testing team finds that the problem still persists despite being marked as resolved by the development team, it indicates a lapse in the developer's responsibility. In such cases, the bug should be reopened, and a record should be made to highlight the ongoing issue. It's important to note that even after an issue has been verified, it can reappear due to various reasons. To mitigate this risk, it is advisable to have automated scripts or tests in place to provide ongoing coverage and detect potential regressions by following these steps. The testing team can ensure that fixed issues are properly validated, any recurring problems are addressed, and the overall quality of the software or system is maintained. The final part is testing summary. When formulating the testing plan, it's vital to establish the specific requirements for the subsequent testing summary. This should include development of a testing operation manual tailored to new technologies. This manual should outline the testing procedures and protocols specific to the new technologies, providing clear guidelines for testers to ensure effective testing. Preparation of case analysis reports focused on instances of errors or failures. These reports should offer a detailed investigation into the causes of the errors and the actions taken to address them. They will be instrumental in understanding common errors and formulating strategies to prevent similar issues in the future. By clearly defining these expectations within the testing plan, the necessary documentation can be prepared and made available for the subsequent testing summary. Thank you for watching the first installment of our Smart IoT Hardware Testing course. We hope you've gained valuable insights into key concepts and skills related to smart hardware testing. If you have any questions, would like to share your testing experiences, or have specific topics you'd like us to cover in future videos, please leave a comment below. We value your feedback and are dedicated to tailoring our content to your needs. Don't forget to subscribe to our channel, like this video, and share it with friends who are interested in smart hardware testing. We look forward to seeing you in the next installment. Thank you.